In mathematics, and particularly topology, a fiber bundle is a space that is locally a product space, but globally may have a different topological structure. Specifically, the similarity between a space E and a product space B times F is defined using a continuous surjective map that in small regions of E behaves just like a projection from corresponding regions of B times F to B. The map pi, called the projection or submersion of the bundle, is regarded as part of the structure of the bundle. The space E is known as the total space of the fiber bundle, B as the base space, and F the fiber. In the trivial case, E is just B times F, and the map pi is just the projection from the product space to the first factor. This is called a trivial bundle. Examples of non-trivial fiber bundles include the Mobius strip and Klein bottle, as well as non-trivial covering spaces. Fiber bundles such as the tangent bundle of a manifold and more general vector bundles play an important role in differential geometry and differential topology, as do principal bundles. Mappings between total spaces of fiber bundles that commute with the projection maps are known as bundle maps, and the class of fiber bundles forms a category with respect to such mappings. A bundle map from the base space itself to E is called a section of E. Fiber bundles can be specialized in a number of ways, the most common of which is requiring that the transitions between the local trivial patches lie in a certain topological group, known as the structure group, acting on the fiber F. Formal definition. A fiber bundle is a structure where E, B, and F are topological spaces and pi. EB is a continuous surjection satisfying a local triviality condition outlined below. The space B is called the base space of the bundle, E the total space, and F the fiber. The map pi is called the projection map. We shall assume in what follows that the base space B is connected. We require that for every x in E, there is an open neighborhood UB of pi such that there is a homeomorphism pi minus 1 U times F in such a way that pi agrees with the projection onto the first factor. That is, the following diagram should commute, where project 1, U times FU is the natural projection and pi minus 1 U times F is a homeomorphism. The set of all is called a local trivialization of the bundle. Thus for any P and B, the preimage pi minus 1 is homeomorphic to F clearly is, and is called the fiber over P. Every fiber bundle pi EB is an open map, since projections of products are open maps. Therefore B carries the quotient topology determined by the map pi. A fiber bundle is often denoted that, in analogy with a short exact sequence, indicates which space is the fiber, total space and base space, as well as the map from total to base space. A smooth fiber bundle is a fiber bundle in the category of smooth manifolds. That is, E, B, and F are required to be smooth manifolds and all the functions above are required to be smooth maps. Examples: trivial bundle let E equals B times F and let pi EB be the projection onto the first factor. Then E is a fiber bundle over B. Here E is not just locally a product but globally one. Any such fiber bundle is called a trivial bundle. Any fiber bundle over a contractible CW complex is trivial. Non-trivial bundles Mobius strip. Perhaps the simplest example of a non-trivial bundle E is the Mobius strip. It has the circle that runs lengthwise along the center of the strip as a base B in a line segment for the fiber F. So the Mobius strip is a bundle of the line segment over the circle. A neighborhood U of a point XB is an arc. In the picture, this is the length of one of the squares. The pre-image in the picture is a slice of the strip 4 squares wide and 1 long. The homeomorphism phi maps the pre-image of U to a slice of a cylinder, curved but not twisted. The corresponding trivial bundle B times F would be a cylinder, but the Mobius strip has an overall twist. Note that this twist is visible only globally. Locally, the Mobius strip and the cylinder are identical. Klein Bottle. A similar non-trivial bundle is the Klein Bottle, which can be viewed as a twisted circle bundle over another circle. The corresponding non-twisted bundle is the 2 torus S1 times S1. Covering map. A covering space is a fiber bundle such that the bundle projection is a local homeomorphism. It follows that the fiber is a discrete space. Vector and principal bundles. A special class of fiber bundles, called vector bundles, are those whose fibers are vector spaces. Important examples of vector bundles include the tangent bundle and cotangent bundle of a smooth manifold. From any vector bundle, one can construct the frame bundle of bases, which is a principal bundle. Another special class of fiber bundles, called principal bundles, are bundles on whose fibers a free and transitive action by a group G is given, so that each fiber is a principal homogeneous space. The bundle is often specified along with the group by referring to it as a principal G bundle. The group G is also the structure group of the bundle. Given a representation ρ of G on a vector space V, a vector bundle with ρ AUT as a structure group may be constructed, known as the associated bundle. Sphere bundles. A sphere bundle is a fiber bundle whose fiber is an n-sphere. Given a vector bundle E with a metric, one can construct the associated unit sphere bundle, for which the fiber over a point X is the set of all unit vectors in X. When the vector bundle in question is the tangent bundle T, the unit sphere bundle is known as the unit tangent bundle, and is denoted at. A sphere bundle is partially characterized by its Euler class, which is a degree n+1 cohomology class in the total space of the bundle. In the case n equals 1, the sphere bundle is called a circle bundle and the Euler class is equal to the first Chern class, which characterizes the topology of the bundle completely. For any n, given the Euler class of a bundle, one can calculate its cohomology using a long exact sequence called the Jazine sequence. See also Wang sequence mapping Tori. If X is a topological space and f XX is a homeomorphism, then the mapping torus MF has a natural structure of a fiber bundle over the circle with fiber X. Mapping Tori of homeomorphisms of surfaces are of particular importance in three-manifold topology. Quotient spaces. If G is a topological group and H is a closed subgroup, then under some circumstances, the quotient space G, H together with the quotient map pi, GG, H is a fiber bundle, whose fiber is the topological space H. A necessary and sufficient condition for to form a fiber bundle is that the mapping pi admit local cross-sections. The most general conditions under which the quotient map will admit local cross-sections are not known. Although if G is a Lie group and H a closed subgroup, then the quotient map is a fiber bundle. One example of this is the Hopf vibration S3-S2, which is a fiber bundle over the sphere S2 whose total space is S3. From the perspective of Lie groups, S3 can be identified with the special unitary group SU. The abelian subgroup of diagonal matrices is isomorphic to the circle group U, and the quotient SU, U is diffeomorphic to the sphere. More generally, if G is any topological group and H a closed subgroup which also happens to be a Lie group, then GG, H is a fiber bundle. Sections. A section of a fiber bundle pi is a continuous map F B such that pi equals X for all X in B. Since bundles do not in general have globally defined sections, one of the purposes of the theory is to account for their existence. The obstruction to the existence of a section can often be measured by a cohomology class, which leads to the theory of characteristic classes in algebraic topology. The most well-known example is the hairy-ball theorem, where the Euler class is the obstruction to the tangent bundle of the two-sphere having a nowhere-vanishing section. Often one would like to define sections only locally. A local section of a fiber bundle is a continuous map F. UE where U is an open set in B and pi equals X for all X in U. If is a local trivialization chart, then local sections always exist over U. Such sections are in one-to-one correspondence with continuous maps UF. Sections form a sheaf, structure groups and transition functions. Fiber bundles often come with a group of symmetries which describe the matching conditions between overlapping local trivialization charts. Specifically, let G be a topological group which acts continuously on the fiber space F on the left. We lose nothing if we require G to act effectively on F so that it may be thought of as a group of homeomorphisms of F. A G atlas for the bundle is a local trivialization such that for any two overlapping charts and the function is given by where Tij, UJG is a continuous map called a transition function. Two G atlases are equivalent if their union is also a G atlas. A G bundle is a fiber bundle with an equivalence class of G atlases. The group G is called the structure group of the bundle. The analogous term in physics is gauge group. In the smooth category, a G bundle is a smooth fiber bundle where G is a Lie group and the corresponding action on F is smooth and the transition functions are all smooth maps. The transmission functions Tij satisfy the following conditions. The third condition applies on triple overlaps UJ-UK and is called the cocycle condition. The importance of this is that the transition functions determine the fiber bundle. A principal G bundle is a G bundle where the fiber F is a principal homogeneous space for the left action of G itself. In this case, it is often a matter of convenience to identify F with G and so obtain a action of G on the principal bundle. Bundle maps. It is useful to have notions of a mapping between two fiber bundles. Suppose that M and N are base spaces, and pi E, EM and pi F, Fn are fiber bundles over M and N, respectively. A bundle map consists of a pair of continuous functions such that, is, the following diagram commutes. This means that is also G-morphism from one G-space to another, i.e., for all in case the base spaces M and N coincide, then a bundle morphism over M from the fiber bundle pi E, EM to pi F, Fm is a map phi, EF such that. This means that the bundle map phi, EF covers the identity of M, that is, and the diagram commutes assume that both pi E, EM and pi F, Fm are defined over the same base space M. A bundle isomorphism is a bundle map between pi E, EM and pi F, Fm such that phi is also a homeomorphism. Differentiable fiber bundles. In the category of differentiable manifolds, fiber bundles arise naturally as submersions of one manifold to another. Not every submersion F. Mn from a differentiable manifold M to another differentiable manifold N gives rise to a differentiable fiber bundle. For one thing, the map must be surjective, and is called a fibered manifold. However, this necessary condition is not quite sufficient, and there are a variety of sufficient conditions in common use. If M and N are compact and connected, then any submersion F. Mn gives rise to a fiber bundle in the sense that there is a fiber space F diffeomorphic to each of the fibers such that equals is a fiber bundle. More generally, the assumption of compactness can be relaxed if the submersion F. Mn is assumed to be a surjective proper map, meaning that F-1 is compact for every compact subset K of N. Another sufficient condition, due to Ehresmann, is that if F-Mn is a surjective submersion with M and N differentiable manifolds such that the preimage F-1, X, is compact and connected for all Xn, then F admits a compatible fiber bundle structure. Generalizations. The notion of a bundle applies to many more categories in mathematics, at the expense of appropriately modifying the local triviality condition, cf. principal homogeneous space and torsor. In topology, a fibration is a mapping pi, EB which has certain homotopy theoretic properties in common with fiber bundles. Specifically, under mild technical assumptions, a fiber bundle always has the homotopy lifting property or homotopy covering property for details. This is the defining property of a fibration.